Here are the solutions to problems 26 and 27 on your review sheet. For number 26, you're going to design a new roller coaster for a ride at Dorney Park. The park wants you to be sure to put a loop in the roller coaster that will thrill its riders. Your job is to find out the radius of the loop for your roller coaster if your riders are going 22 meters per second. There's our speed. When they are at the top of the loop and they are to experience a moment of weightlessness. When at the top of that loop. Now, weightlessness means that you are free falling, that you're for a moment not touching your seat. So the only force acting on you is the force of gravity. You might say, hey, if you're weightless, would gravity act on you? Yes, because gravity never ever goes away. To feel weightless is almost like you're jumping out of a plane. You are free falling. And that's what's happening here at the top of the loop. So in this particular situation, the force that points towards the center is gravity. So gravity is my centripetal force. For gravity, I'm going to use m times g because we are on Earth, so we can use g as 9.8. It's not an orbiting space problem. And then here for centripetal force, I'm going to use mv squared over r because I have v and I'm looking for r. The m's cancel because mass is irrelevant on a roller coaster. From here, we're going to solve for the r. So I'm going to multiply the r up over here to the left. So I'd have r times g, and then I'm going to divide g down to the right, which is why I have v squared divided by g. Plugging in my numbers, I get 22 meters per second. Don't forget to square it, divided by 9.8 meters per second squared. So I get a radius of my loop of 49.4 meters. Number 27, it's another amusement park ride. You're going to design another ride for the people at Dorney. They want to have passengers spin inside of a circular room and stand against the wall. The room then starts to spin. They want to make it so the floor drops out when the ride is going at its maximum revolutions per second, and yet the riders don't slide down the wall. I believe this ride might be called the Gravitron at some amusement parks. Given the parameters that the ride is to have a radius of 4.8 meters, and that the coefficient of friction between the passengers and the ride is going to be 0.12, which is a pretty small coefficient of friction. So they're saying the slipperiest it could possibly get is that. What is the minimum speed required so that people do not slide down the wall? So we're looking for speed here. Well, this one's a very important one to have the drawing. So here's the person, there's the wall, and the floor is down here. So what forces are acting on them? Gravity always acts downward. Well, if they're up against the wall is pushing back, and we're going to call that a normal force because the normal force is two surfaces in contact. And now, which way would the person slide? The person would slide down the wall if given the opportunity. So if you're going to try and slide down, then friction tries to prevent that by going upward. So which force points towards the center of our circle? In this case, it's going to be the normal force. That's going towards the center in this circular ride. So my normal force is my centripetal force. So now, if I want this person to not slide at the minimum speed required for this person not to slide, my force of friction upward is going to be equal to my force of gravity downward, because then everything is balanced and there's no acceleration down the wall, no sliding in that situation. So friction's got to equal gravity. The faster I go, then friction would get even bigger than gravity, but I'm talking the minimum speed, so right when they're equal to each other. Well, we have one equation for friction, which is mu times the normal force, which we're going to use because we have a mu. And for force of gravity, we're on Earth, so we can use m times g. Well, I'm trying to solve for velocity, and I'm just going to get normal force here by itself. So I'm going to divide the mu over to the other side, getting me mg over mu. And you might say, wait a second. I don't have a velocity yet. Well, that's fair, but my normal force is centripetal force. Remember, that's the one that goes towards the center. So instead of writing normal force, I can write centripetal force, which means every equation that we have for centripetal force on our equation sheet is describing the normal force, which means that the normal force, which is centripetal force, is mv squared over r. So mv squared over r equals the stuff that was on my right side, which is mg over mu. I have m on both sides of my equation, so they will cancel out, leaving me with v squared over r equals g over mu. I'm trying to solve for the v, so I'm going to multiply the r over to the right side, which is why it's in the numerator down here. And I got to get rid of that squared, so I'm going to take the square root. Plugging in my numbers, I now have the square root of g, 9.8 meters per second squared, times the radius, 4.8 meters, all divided by that minimum coefficient, 0.12. And I know that the riders have to be going 19.8 meters per second, otherwise they will slide down the wall.